in BGP, then the lower metric, the lower met is going to win. Number 7, I can skip. Number 8, this is important if you have a bigger network with a lot of routers. So OSPF or IGP actually is going to help you to figure out the closest exit. If you do hot potato, you dump off the traffic as close as possible. And yeah, the example here appearing in 3 locations with the same peer, let's say AM6 DKIX links, the big 3 in Europe, they all have the same AS path lengths. So you can if you route traffic, let's origin in Switzerland, traveling to DKIX is the closest in Frankfurt, so we use this exit. And then the number 9 to 13, I highly recommend to make the decision which path to use before number 9 to 13, because it becomes unpredictable, especially if you have choose by a lower router ID, lower cluster ID, or lowest neighbor address. You can just actually do a random traffic path selection or a random best path selection. So this is very short the theory about the BGP best path selection, but what does it mean for us? Probably for you it doesn't mean much, because I assume most networks are eyeball, as I said, so they have probably a ratio of 1 to 5 or 1 to 7 in preference of inbound traffic. So you don't really care too much where the traffic you origin or you're originating is leaving your network, because it's not relevant for cost, it's not relevant for capacity. But it's still good to get a clear idea where the traffic is leaving your network, because it helps in debugging, and if it's predictable, it's better than if it's just happening. The thing is, why I'm talking about these slides is you need to know how content networks distribute traffic which is reaching your network. So you need to know, you need to understand how they manage their outbound traffic in order to be able to manage your inbound traffic. So I come again to this slide, it's almost the same. The route map transit out is affecting your inbound. I have here a sample network. So we are AS4, an eyeball heavy network, and AS4 is buying transit from AS1 and AS2 in this example. Then we figured that AS3, which is a huge server farm, sends massive amount of traffic, call it YouTube or whoever, towards your customers, your eyeballs. So I made the assumption that AS3 is about 40% of the whole traffic of AS3 sends about 40% of the whole traffic towards AS4. So as a matter of fact, AS3 has peering with your transit AS1. AS3 is also buying transit from AS2, which is also your transit. And the problem is AS3 prefers the path via AS1 towards your traffic, towards your network. So that makes that your transit link towards AS1 is congested, and AS2 to AS4 is almost empty. You have available capacity. So how can you load balance this? AS3 prefers, because it's a cheaper or a peering link, so it's cheaper for them, the path via AS1. So AS3 prefers this path because it's a peering. They see this as a peering, and this is cheaper for them, so they set here a higher local pref and exit all the traffic towards AS1. Makes you this link congested, this one is empty. The AS path is actually just the same length, but still all the traffic flows here. What can we do? Well, first guess would be peer with AS3. And if this is a content-heavy network like Google, they probably would be happy to peer with you. But so you set up an email, dear peering coordinator of AS3, please peer with us because we have a lot of traffic, and yeah, that's it. As long as you're in the same location, that's cool. They happily peer with you, or you're connected to the same internet exchange. You talk to them, or you send a mail, and that's it. But we need to assume that AS3 cannot peer with AS4 because they're not on the same location. And then there would be a requirement of a long-haul transport capacity to interconnect directly. Like a wave or an STM whatever pipe, which is expensive. Someone would have to pay that. So if you cannot do that, what else can we do to balance traffic between AS1 and AS2, our two transit links? Second guess, prepending. We make the AS path longer towards AS1. Okay? So AS3 then sees 3 AS hops via AS1 and 2 AS hops via AS2. If BGP just makes the decision, then BGP would choose AS2 because it's a shorter AS path. But it's a little effect. Why? AS3 keeps using the path via AS1 because it's still cheaper for them. They don't care about AS lengths because they overrule it with a local pref setting, and the traffic keeps flowing that way. There will be probably some rerouting of the rest of the world traffic. If you go back to the sample network, there's other traffic flowing in here, which are probably then choosing AS2 instead of AS1, but there is no guarantee. So the congestion probably would remain just the same or be a little less. Okay, what can we do then? More prepending, yes. So we prepend 3 times. But still, the local pref of AS3 keeps routing traffic via AS1. And now here comes the moment where we can distinguish between the clever and the stupid peering coordinators. So I'm going to show the example of the stupid ones, massive more prepending, the full blast. And as a matter of fact, the result is 0, but if you look at the routing table of the global routing table, we have a lot of this crap. It's not a joke, it's reality. We have such long prepends in the global routing table, which is simply stupid, and it shows nothing than the inability of the peering coordinator of the respective AS. Rule of the thumb, if 3 prepends don't help, more prepends won't either. Just avoid it, please. Okay. So, what can we do? Let's assume AS4, so ourselves we have two networks, 1/13 and 1/16. So we propagate these, we start propagating selectively. We could actually propagate the /13 only towards AS2. The /16 and the /13 we propagate only to AS2, and the /16 are going to be propagated to both networks. So AS3 sees our larger portion of our larger prefix only via AS2 and starts using it. They are probably not too happy because they have to use transit capacity now and pay more to their transit provider AS2. So AS2 is happy certainly because they get more money. But there is also a drawback in doing this. You have less redundancy. You don't have consistent routing anymore, which makes debugging more difficult, and it's not scalable because if prefixes aren't equal, or let's assume if you have one prefix with 90% of all your customers, and then you have 10 other prefixes which has the rest, it doesn't scale. So how can we make this a bit more scalable? We can start advertising more specifics. So we have a /13 network, we have a /16 network, and we chunk them into 10/17 networks and advertise to each of our transit providers just 5. To AS1 we advertise 5/17s and to AS2 as well, and the traffic get balanced. So AS3 sends about 50-50% towards my network via AS1 and AS2. So mission completed. We have a rest now? Probably not. What if AS1 breaks? Then half of the networks will be invisible to AS3. Not a good idea, because if you do that, it breaks redundancy. All right, we can avoid this when we just keep the the /13 and the /16 in the network table, and we propagate those as well. The traffic remains balanced because a more specifics always wins over a less specific, regardless of the local pref. So finally we managed to balance the traffic flowing from AS3 to AS4, and well, yeah, it's a possibility how to do it, but not really. It's not a clever possibility. We are halfway there. The thing is, deaggregation is normally not recommended. The global peering community strongly advises not to use deaggregation. It increases BGP routing table unnecessarily, which means more BGP updates for everyone globally, more CPU cycles, higher memory requirements, and higher hardware costs. The global peering, the global BGP table contains today approximately 350,000 routes. And if everybody would neatly aggregate, it would just be about half of that amount. And in red, the example I gave with cutting a /13 and a /16 into 10/17s is pretty stupid. Because the same effect could be reached by deaggregating into 2/14s and 2/7.